Hi everyone, my name is Nikhil Taroni, Head of AI Products at gcore. First of all, thank you very much to the organizers of Conf42 for having me here today. And I'm really excited to talk to you about our pioneering work building our global intelligence pipeline and its cornerstone technology, Inference at the Edge. And during the talk, feel free to ping me on Slack with any questions or comments, and I'll do my best to answer. But for now, let's dive in. As I'm here on behalf of gcore, let me begin by telling you a little bit more about us. We are a global cloud, edge, and AI solutions provider headquartered in Luxembourg, but with a global presence. And our vision is to connect the world to AI anywhere, anytime. The cornerstone of the company is our secure low latency network, which consists of over 180 CDN points of presence and 25 cloud locations, giving us an average response time of just 30 milliseconds. We offer a range of cloud services, covering infrastructure as a service through to platform as a service. But today, as we are at a machine learning conference, I'm going to focus on our AI as a service offerings and some of the work we've done there. To begin, we offer a range of AI services, including GPU bare metal and virtual machine instances, managed Kubernetes clusters, and also a 5G platform that helps reduce the latency between your device and a model. But all of these services underpins what we call our global intelligence pipeline, which is designed to follow the steps taken by machine learning practitioners to train, deploy, and scale AI applications in production. So starting on the left there, you can see that we offer direct access to high-performance AI infrastructure backed by NVIDIA GPUs. This provides the raw computing power needed for intense AI training workloads. We then also offer a managed Kubernetes service, which can also then utilize the GPU nodes to help you orchestrate your machine learning and AI workloads. So we then enable the deployment of workspaces in MLOps platforms from our vendor partners, and this helps you manage your machine learning lifecycle. And finally, we specialize in the serving and inference of pre-trained AI models, and that's going to be the focus of my talk today. So as many of you know, when it comes to training your large machine learning AI models, you really care about compute performance in order to accelerate your research and development. So to give you the best possible performance, we partner with NVIDIA so that all of our GPU clusters are powered by 808 A100 or H100 GPUs with NVLink. But for really large training jobs that span multiple compute nodes, it's equally important to have a very fast interconnect, providing direct GPU connection across multiple nodes. All of our clusters are also connected with the latest InfiniBand. But now once you've trained or perhaps fine-tuned a large model for your use case, the question arises, where can I serve my model with low latency? This is a really important question for several reasons. The main one being because as you go from research and development to production of a business application of AI, your primary compute workload will move from training to inference. For many business-critical applications, the end user needs a real-time response, no matter where they are in the world. And this is becoming more and more important as the market is, of course, rapidly evolving with an increasing number of businesses not only testing out AI in pilots or proof of concepts, but actually adopting AI applications in full-scale production at enterprise scale. So as an example of that, you can see here a survey last year from McKinsey, from enterprise leaders, and it showcased how over half of them are already adopting AI. And again, it just showcases just how prevalent AI is becoming, not only in pilots, but in actual production. This not only drives the demand for inference compute, but also the need for scalable, reliable, and secure infrastructure that can maintain a very high level of service availability. So to give you an example, the application most of us are most familiar with is probably chatbots. So taking an example here, you can see that if you take an off-the-shelf model, such as Mistral 7B, and run that locally, and I've taken a reasonably standard question, around about 200 tokens, and got an answer around 20 tokens back. And running that locally took around about 250 milliseconds. Now, to an end user, that really feels like real time. But now, supposing you were sitting, say, in Tokyo, and you were submitting that request to a data center in the cloud in, say, the United States, then just the network latency could easily double or treble that at that time, so that when you then add in also the inference time, the end-to-end processing could get close to a second, which would really damage the user experience. Of course, there are many other use cases where you really care about a real-time response, whether that's, for example, autonomous driving, or any sort of virtual live streaming, or even quality inspection use cases in industries such as mining or manufacturing. For all these applications, you of course need high-performance compute for the fast inference, but you also need very low latency. And in many cases, it's also important for regulatory or privacy reasons that the data is processed locally. And for us, that means in an edge location that is geographically close to the end user. So now supposing you're looking to run inference of your model, if you want to achieve that in real time, then there are 3 core requirements you have to work on. The first of those is you need a distributed, powerful compute infrastructure around the world. But also you then need a very low latency backbone which connects that compute. You then also need runtime deployment and reconfigurability. So let's start with the inference. And when we've looked at running inference at the edge, here at gcore, we faced several challenges that required innovative solutions to help optimize performance and efficiency. I'll focus on LLMs here, as they are the probably technology that gets the most attention in a minute. But of course, these techniques are also relevant to other technologies. So the first strategy that we used was operator fusion. And by merging edge-facing operators, this helps streamline computational tasks, which often leads to better latency and enhancing the responsiveness of AI models. We also employed quantization, which involves compressing the activations and weights of neural networks, so they require fewer bits. And another strategy is compression, with techniques such as sparsity, where we trim unnecessary connections, or distillation, where we train smaller models to mimic larger ones. And of course, with all these techniques, you've also got to balance the performance of the model with the accuracy and making sure you don't lose too much accuracy. And finally, the fourth technique, of course, is very well suited to GPUs, is parallelization. Typically, we've implemented tensor parallelism, distributing computation across multiple devices, and also pipeline parallelism to help efficiently manage larger models and help scale up our AI capabilities. So once we've optimized the compute of the model, the second piece of the puzzle is network latency. Now on this slide, I'm just showing you a map which shows the growth of 5G around the globe. And the reason I'm showing that is, of course, over the last few years, 5G has enabled many of us, perhaps all of us, to stream really high quality content, such as videos, straight to our mobile devices because of the ultra low latency that 5G provides. So we've taken those learnings, looked to apply them also to AI. And so by leveraging our CDN network with 180 points of presence, what that means is that a user request will take just an average of 30 milliseconds end to end to get to our network and back. And then perhaps a total of around 50 milliseconds to then get to an inference node where the actual machine inference takes place. And so that round trip of around 50 milliseconds, very fast compared to perhaps a few hundred milliseconds in a typical public cloud setting. So what that means is that provided you've also optimized the model inference so that it takes perhaps between 100 and 400 milliseconds, you can achieve an end-to-end processing time of under half a second. And that's important because around half a second is around about the time which, as a human, we perceive that to be in real time. Any slower, you start to notice that lag. So again, to put that into more context, I said, if you combine a very low latency network combined with an optimized inference, round trip in under half a second, and that's applicable to a number of technologies. So, for example, automatic speech recognition, object detection, or text-to-speech are all examples where this enables a real-time response. So then the final piece of the puzzle we've had to work on, runtime deployment and reconfigurability in a simple and scalable manner to really enable this inference at the edge at scale. So to do this, we achieve this using a container as a service technology, so that we provide a single Anycast endpoint that can be easily connected to a developer's application. So what that means is that no matter where in the world an end user is, the request to that endpoint is routed to the nearest CDN node, and from there to the nearest inference node. So if we delve into a little bit more detail, you can see what's happening here under the hood. I apologize, it's a little bit small, but hopefully you can follow it. So at the top here, supposing you have two end users, and let's say one of those is in Rio de Janeiro, and one of those in, say, Kyoto. Now, the Anycast endpoint is available globally. When each of those users sends the request, that request will go to their local CDN node. The user in Kyoto, there might be a CDN node in Kyoto itself, and similarly for Rio de Janeiro, that request would go to the Rio de Janeiro CDN node. Now, after that, we developed smart routing technology, and what that does is it routes the request to the nearest available inference region. So that's where we have some high-performance compute, typically GPUs, that will do the actual optimized inference. Now, what that means is that not only does it guarantee the fastest response time for each of these individually, but it also ensures that the processing and the model itself also stay locally. So in particular, the user in Kyoto, the inference will be in, say, Tokyo, and their data and that model will only ever be in Tokyo. And likewise for the user in Rio, in Brazil, their model and their inference will also take place locally in Brazil. That also actually means you could potentially have a different model in each region. So for example, you could have a model that was trained only on Japanese user data in Japan, and similarly for other world regions. And so that also helps maintain that sort of data privacy and locality that I was talking about earlier. The final piece of the puzzle that I want to talk about here is that in each of these regions, we also have developed auto-scaling functionality. So what that means is that the amount of compute scales up and down with demand. And that's really important because it means that you can scale up the compute when you need it, when there's lots of demand. But equally importantly, you can scale back down again when there isn't. And also that means that you're not then paying for compute when you don't use it. So tying all these things together, I'll just summarize by putting together our sort of full end-to-end architecture. And you'll see that we've combined high-performance AI training infrastructure. And then that could be in a public cloud setting. For some customers where privacy is really important, we could also offer it in a private cloud setting. And then if you combine that with this inference set, this low network, and the inference at the edge technology that I've spoken about today, you have a comprehensive global AIoT architecture that we believe is fit for today's most demanding and scalable AI applications. So with that, that's probably enough of me talking. What I'll showcase here are a few demos that showcase technology in action. So the first of those is an example with a real-time face avatar. And what you'll see here is that at the top here, I'll be entering in some prompts. And what you should look out for is the way that the avatar of the person changes in real time as I type in those prompts. So for example here, I'm going to type in a portrait of Elon Musk, and you see that the face has changed to Elon Musk almost immediately. And now as I type Bill Gates, again, that change was done in real time. And now moving on to Madonna. And there's a few more examples here, but again, what's really impressive is the way that the change is done in real time compared to the typing of the prompt there. And there's a Jeff Bezos when he had hair. So another example I can show you here is of a real-time translation from English to Luxembourgish. Now, like most people in the world, I don't speak Luxembourgish, which is a local language of Luxembourg. But if I was in our head office and I needed to quickly translate something, then no problem. I could use a typical translation tool.
Hello there. Allow me to introduce myself. I am an advanced machine learning model specifically designed for voice-to-text translation from English to Luxembourgish. I have been created and powered by the cutting-edge technology of gcore AI Cloud.
Great, and I'll press send, and you'll see that, again, in less than a second, less than half a second, I'd say, the translation happened, and I've received the Luxembourgish translation of those words. And again, that really showcased from the minute I pressed send, the processing was in almost real time. So in the final example I'll show you today is some work we've done with our colleagues at Let's AI. Let's AI are a creative platform that allows you to generate images for anything you know simply by tagging it in a text. We've worked with Let's AI over the last few months, and they've been utilizing our H100 AI infrastructure and inference services to both train their GenAI models and also serve them to their customers worldwide. So what you see here is an example of a single image that was generated by the platform. But I think what's really impressive is that you can actually take a series of images generated by the platform and then combine them together to form a video. So this is an example of a video generated with Let's AI, and which I think really shows the power of generative AI powered by GPU infrastructure.
The rookie sensation Ricky Malone surprises with an unbelievable pole position at Silverstone.
It looks like Ricky Malone is joining forces with the legendary F1 team for the 1986 season.
Ricky, after our crash, watching you lose yourself was hard. Not just because of us, but seeing you give into darkness. It wasn't only about you. I was hurt too, trapped by resentment. Encouraging you to race again, to face that trauma. It's for both of us. I need to see you conquer this. Not to go back to what we had, but to find closure, for both of us to move on. This is about letting go, forgiving each other, healing. By helping you return to the track, I'm also finding my way back. It's about finding peace, Ricky, for you and for me.
So there you go, a completely generated video that I certainly found very impressive. So we're almost at the end of the talk here, and just wanted to let you know that if you're interested in learning more about technology, our Inference at the Edge product is actually being launched in beta this week. So this lets you deploy your model globally with a single endpoint, as I explained. Or you can also choose an open source model out of the box from a model catalog, which includes popular models such as Mistral and Stable Diffusion. So this gives you a serverless AI compute with very low latency around the world on a pay-as-you-go model with DDoS endpoint protection. But also, as this is our beta service, it's also free. So if you'd like to try it, I'd love to hear from you, find out about your machine learning use case, and see whether edge computing could be the right solution for you. And I'll just end saying that, of course, our work doesn't end here. The team is striving to push the limits of our network and bring down the latency to just a few tens of milliseconds. And we believe this will further benefit sort of really mission-critical use cases of AI at the edge. So with that, I hope you've enjoyed the talk. Thank you for joining me today. And again, please do reach out if you have any questions or would like to discuss any of the technologies that I've spoken about today. But for now, have a great conference